which of the following is a differential equation that correctly describes Newton's second law for a simple harmonic oscillator of mass m and restoring force constant k? In other words, this thing, with Newton's second law being F equals ma, net force equals mass times acceleration, and the spring force equal negative k delta x. K is the spring constant, delta x is the displacement. The negative is not a problem. The negative should not disturb you. All we're saying here is that if you push against a spring, it'll push against you. If you stretch a spring, it'll pull itself back. It'll be always fighting against you. The force from the spring always fights against the displacement. If you push a spring to the left, it'll be pushing back to the right. That's what the negative means. You ever met a negative person who's always against whatever you do? Anyway, the answer is B. This is true because acceleration, of course, is the second derivative of position, d2x dt squared. And we like this as an answer because we know that for simple harmonic motion, this is a big deal for other problems, the acceleration is always proportional to the displacement, but in the opposite direction. Acceleration, that's what B says there. Acceleration proportional to displacement, but in the opposite direction. A physical pendulum oscillates through very small angles about the vertical with the angle measured in radians, obeying the differential equation d2 theta dt squared is equal to negative 4 pi theta. What's the period of oscillations? Well, here is a simple harmonic type of equation. I know one when I see one, and I know that this is simple harmonic motion because it's just like a spring. It might not look just like a spring, but isn't force equal to mass times acceleration? And there we have a second derivative in the opposite direction and proportional to the displacement. Simple harmonic motion at its best, and the acceleration in the case of our physical pendulum here is equal to 4 pi times negative x. Again, proportional in magnitude, opposite in direction are the second derivative and the displacement. And we know something else about acceleration. It has a maximum quantity equal to amplitude times omega squared, or equal to quantity 2 pi f squared times the amplitude. You just can't accelerate any greater than that, and your acceleration is the greatest, of course, when your displacement is the greatest. Like we said, this is simple harmonic motion, don't you know? So all we need to do is plug the two together. Frequency is equal to 1 over period, of course, and we're looking for period. So we're plugging those two equations together and solving for period, which is really kind of complicated. When you're solving for period here, again, you get all the way to the end of the problem and your head spins. If you want to give yourself a little mental break here, you can just plug in A, B, C, D, and E for T, for period, and D is the one that'll work. A simple pendulum, initially making an angle of theta with the vertical, is released from rest during the first half period of the motion. The graph that best represents the magnitude of the tangential acceleration of the mass as a function of time is which of the following? Well, we know that tangential acceleration should be proportional to displacement, but in the opposite direction, so that will be graph C. Acceleration is greatest when you're furthest away from the equilibrium point, and then it goes to 0. The tangential acceleration is 0 when you're at the equilibrium point, and I make a point to focus on that word tangential because this is a two-part problem in the test I took it from. Another question asks about your centripetal acceleration, and that would be graph D, showing your centripetal acceleration. Pendulums are tricky. Tension, they got centripetal acceleration. So again, graph C answers the question asked here about tangential acceleration, and graph D answers the question about centripetal acceleration, which is v squared over r. Velocity is a maximum. Of course, velocity is a maximum as you swing through that equilibrium position. Two identical springs with spring constant K are connected as shown in the figure, and a mass m is attached. When the mass is displaced from equilibrium, the period of oscillation, yikes. To answer this, we'll need to focus in on the spring and the spring constant. There's the equation, which means that if you pull on this spring with a force F, it'll stretch a little bit. That's a displacement delta x. But when you put two springs in series. We'll call these two springs in series. Do you see that? It stretches twice as far. It stretches twice as far, and that means that the effective spring constant is half as much. If you don't believe me, draw a box. The force of the spring on the left on the spring on the right is the same as the force of the spring on the right on the spring on the left, and they both stretch the equal amount. So the overall stretch is double, so the overall spring constant, the effective spring constant, is half as much. This is different than if we were to put these springs in parallel. If we were to put these springs in parallel, they would join forces fighting against the pole force. They would each stretch half as much. The overall stretch would be half as much. The effective spring constant would be twice as much. What am I talking about? I'm talking about 1/2 k for this problem. Plug that into your equation for the period from the equation sheet. And C is the answer. A particle moves in a circle. This is a two-part question. A particle moves in a circle in such a way that the x and y coordinates of its motion given in meters as a function of time t in seconds are x equals 5 cosine 3t, y equals 5 sine 3t. What is the radius of the circle? Sketch a quick circle there. Remember that circles and waves are connected with cosines and sines, so what are we saying here? That the horizontal displacement oscillates back and forth in a simple harmonic motion type of way, a cosine type of way, and the vertical displacement oscillates back and forth as well, and the amplitude of those oscillations are 5. The radius of the circle is 5 meters, C. But which of the following is true about the speed of the particle? Well, we have horizontal displacement and vertical displacement. In order to find velocity in the x direction, velocity in the y direction, we will need to take derivatives of the cosine and the sine functions. Don't worry, we can do this with the equation sheet's help, and there are the derivatives. But we want total speed. Let's find the net velocity with the Pythagorean theorem. We got 15 squared and 15 squared, so we can factor that out. And then apply everybody's favorite Pythagorean identity. And you'll agree that the answer is B. But did they really expect you to do all those steps? What do we have to do there? We took two derivatives, and then we used the Pythagorean theorem, and then is this a 4-step problem with and they don't even list the Pythagorean identity on the equation sheet. So do they really expect you to go through all those steps? Well, I have no idea what's in their heads. I mean, you could just think about the speed here and there. It's 15 there and there, and then B is the only answer that'll work. I guess you could do it that way.